So today we'll talk about multi-phase flow modeling. That's another very important topic, especially since that is used in the industry nowadays. That's the latest stuff that's going on in CFD. And then we'll also talk about briefly finite element method for fluid flow modeling. Till now what we have done is we've talked about finite difference method, finite volume method, and we'll just touch upon the finite element method. And the code that I'll be using to demonstrate this multi-phase flow solver today for you is going to be an FEM code. So you can see that FEM codes can also give us good results. Right, so let's start with the first section of this presentation on the multi-phase flow modeling. Now multi-phase flows are flows where you have more than one phase. So you could have a liquid along with a gas, you could have a liquid with a solid or a gas with a solid. So liquid and gas is typical applications of bubbly flows where you have some gas, sometimes you have some vaporization happening inside the fluid and so on, some cavitation, etc. Solids in a liquid is a slurry flow. Typically in industry you would see that you will mix solids with liquids to make a slurry out of it so that you can have the solids flow. And gas and solid typically seen in fluidization applications where you tend to fluidize your solids using gases, or when solids sort of fall into a heap, for example, from some hopper, then you would see that it tends to create some cloud, some air flow happens around it. So these are typical applications. You can also have applications where you have all solid, liquid and gases existing together. So we need to model their movement, their flow, the movement of particles, the movement of bubbles, the flow of fluids, the flow of air inside the bubbles, the flow of liquid as such overall. So we need to use some sort of fluid flow modeling for modeling these flows. The typical approaches we have are either Eulerian, where you model the fluid like a fluid, like you have been doing in the Navier-Stokes equation. In a liquid, for example, in an Eulerian approach, you try to find out at a given point in space, find out the velocity as well as pressure. Whereas in the Lagrangian approach, you tend to follow a particle typically. So in a Lagrangian approach, if you are dealing with, let's say, bubbles. So in Lagrangian approach, you will tend to follow a given bubble. So let's say you have 3 bubbles to start with, Lagrangian approach will follow the bubble. So bubble number 1 has a speed or a velocity of v1, an acceleration of a1, a position vector of x1. Similarly, bubble 2 has certain properties. So that's a Lagrangian approach. But you can also use an Eulerian approach to model bubbles or particles. For example, if you have a collection of bubbles, lots of them, then what you would say is that at this point in space, around this point in space in a given small control volume, you have this fraction of bubbles. The average velocity of bubbles at this point in space around this point in a small volume is v, for example. So you can also use an Eulerian approach to model particles which are flowing by using some sort of an averaging approach. Okay. One of the most important things which also results in modification of your equations is the interphase interaction. So when you have, let's say, particles in a fluid, so let's say some particles are falling in a fluid. So what happens is, if you look at the fluid, a particle falling in a fluid will tend to apply a downward force on the fluid, right? The fluid will tend to get pushed down. Similarly, a particle that is falling in the fluid will tend to be pushed up with the same force because of Newton's third law. So what happens is, there's an interphase interaction between the different phases, and that is what you need to model appropriately or accurately or properly so that you can model the physics accurately. So that interphase interaction is one of the most important terms to correctly predict the physics in multi-phase flows. And then we'll see that typically we'll talk about multi-material and multi-phase flows. So when we say multi-material flows, they, as the name suggests, you have 2 different materials or more than one material which are clearly separate from each other. Okay. So in some applications you have a clear interface between the materials. For example, you have water which is flowing, let's say, in a river. So above the water you have air, and below the air you have water. So there is a clear interface. Now it may happen that sometimes the water may slosh, so the interface may change with time and spatial positions, but you still have a clear interface. And in the other case, you have sometimes you have interpenetrating flows, like you have lots of bubbles in a fluid, in a liquid. In that case, although you have clear interfaces, but there are so many that we don't tend to track the interface as such, because that becomes a very expensive problem, because you have lots of bubbles and you have, let's say, 1,000,000 bubbles in a tank. Then tracking the interface of each and every bubble becomes a very expensive task, because the amount of interface, the area of interface is much large in that 1,000,000 bubbles. So in that case, we tend to use the multi-phase approach. These are just terms, but you would see multi-material versus multi-phase. I will talk about the equations in a while, but we must understand that there is a difference when these terms are used in the literature. Well, then comes turbulence modeling. So you also have to understand how and where to model turbulence if you have more than one phase. So for example, if you have a mixture of liquid and gases, so in that case you would say that you know what, there's a lot of turbulence being generated in the liquid phase, although if you see the velocity field inside a bubble, if you could do that, you'll see some sort of fluctuation inside that as well, but they are highly correlated with the fluctuations in the liquid. So what you do is you tend to solve for K epsilon model for the liquid, and then you develop some sort of a correlation or some sort of an analytical relationship between the turbulence properties of the liquid and the turbulence properties of the gas. So in that case, it becomes sort of a turbulence existing, or you're solving for turbulence in one phase. Sometimes you would see that you need to solve, if it's a multi-material flow where you have a liquid and a gas and they're moving quite separately in terms of inside liquid, the physics is very different from what's happening inside the gas, then you would tend to model turbulence separately for the two. So one has to make a decision as to how to model turbulence in which phase. So next we'll talk about the multi-material flow, and that's very commonly used in situations, as I said, where you have a clear interface. For example, in a glass you have a liquid and a gas. In nature you have water flowing in a river and applications like this. So what happens in this kind of an approach is that we solve for the momentum equation for a single phase. So basically what we say is that at a given point in space, or in any given volume, typically we will see that there will be only one phase, whether it will be a liquid or a gas. Let's say you're talking about a liquid gas situation. So that means that you only need to solve for one momentum equation. But when you solve for a momentum equation, you can have situations where you have a mix, because whenever you deal with an interface, that is where you have a mix. So in that case, what we say is that we are defining a quantity called volume fraction, that's denoted by phi here, this quantity phi here. And this quantity phi is defined in such a way so that in a given volume, the sum of volume fractions of all the phases is equal to 1. So as the name states, it's a fraction of the volume taken by a given phase in a given control volume. And we will track the movement of this volume fraction using the advection equation for volume fraction as given here. It's very similar to a typical 1D convection equation. So this is used to track the volume fraction. So if you have two phases, you will track the volume fraction of one phase, and the other phase volume fraction simply becomes 1 minus the volume fraction of the first phase. And then we will solve for the momentum equation, a common momentum equation, which where the quantities will be weighted using the volume fractions. So for example, if you are dealing with a control volume where you have two phases, so you say that the net density that you have in that phase while solving the momentum equation is actually weighted by the volume fraction. So you have to include density in the equation in that case. Okay. I have not written the momentum equation here, but you can have a look at it. It's very similar, except that you have the effect of density and volume fraction in the momentum equation. So this is how the volume fraction effects percolate into the equation. So if you have more liquid than a gas, then density will tend to be closer to the liquid density. If you have more gas than the liquid, then it will be vice versa. Now one thing we have to particularly note about this multi-material or the volume of fluid method, as it's called sometimes, that you have to resolve the interface, right? That's the reason you are doing this, you're following this approach. So in that case, one needs a very fine grid near the interface to be able to resolve it, because you have a coarse, if you have a coarse grid, then you will not be able to resolve the interface well. and if that's the aim, then one should have a very fine grid. So these methods tend to be expensive in general if you're dealing with large volumes. Now the other method, the multi-phase method, also known as the Eulerian-Eulerian method. Let's say we're talking about two phases, so in that case you will model both phases as Eulerian phases. So that means that you will be modeling them as fluids. So in that case we also define a volume fraction. In this slide I've denoted volume fraction with alpha. That has the same meaning what the volume fraction had in the previous slide, that was denoted by phi. And I've also written the momentum equation in this case, but these equations are solved for each phase. So what that means is this subscript I that you have here, that's actually for the phase. So I can take values between 1 and 2 for this 2-phase problem. If it's 3-phase problem, it can be 1, 2 and 3. So each phase will have its own momentum equation. So these methods will tend to become expensive if you're dealing with because you're dealing with separate momentum equations. You have to solve separate momentum equation for each phase. And this is that interphase interaction term. All other terms are very similar to what you have in single phase momentum equation, except for this Fi, which is the interphase interaction term. And typically one of the most important interphase interaction terms is called the drag force. There are others as well. So the drag force typically is modeled like this, which, as you can intuitively see, that it is because of the difference or the relative velocity between the phases. Because drag between two phases will only exist if one phase is moving relative to the other, right? And then you have some sort of a drag coefficient like you have in single phase flows in fluid mechanics, and that drag coefficient is a function of Reynolds number or not, depending on your Reynolds number values. So if the flow is high Reynolds number, then the drag tends to become constant drag coefficient. If the Reynolds number is low, it becomes a function of the Reynolds number. But that's just one drag coefficient, and these drag coefficients are obtained semi-empirically, in the sense that there is some amount of physics and some amount of experiments being used to get to these relationships. For example, this power of 0.687 definitely was not obtained from physics, it was obtained from some curve fitting of the data obtained from experiments. So of course, better experiments are performed with time. This is a very old relationship called the Schiller-Neumann drag coefficient, that's not even used nowadays, but typically used for testing things, but not for modeling real world phenomena. So you have better models available, but they are a bit more complex in understanding, or the relationship is more complex. So that's the reason I've shown you the simplest one. But typically they will be functions of Reynolds number or some other parameters like bubble or particle shapes or their sizes and so on. So it will have a lot of effects of those things as well. So what are the challenges with multi-phase flow modeling? Well, there are many. One of the major challenges with bubbly flows particularly, which are used very commonly with interface with the multi-phase flow applications, is the bubble coalescence and breakage. So when you tend to use an Eulerian method, then one has to understand the physics of bubble coalescence and breakage, and that is linked to your liquid flow. Because if the liquid flow is like slightly turbulent, then that creates that gives the bubbles a lot of chance to interact with each other, right? And then if the flow becomes too turbulent in the liquid phase, then the bubbles tend to start breaking. So there's a lot of interaction between the bubbles and the liquid in terms of the bubbles being bubble coalescing or breaking. Similarly, similar stuff can happen with particles, solid particles as well. They can agglomerate because of interaction with each other in a turbulent continuum like a liquid. Depending on the properties of the solids, if they tend to agglomerate, or they can break. So they may interact with each other. Solid particles may hit other solid particles and they may break. So you have to understand, or one has to figure out how to model this physics to be able to simulate the real world phenomena in multi-phase flows. So that's a big challenge. Of course, work has been done, but we are not there yet. As I said, that drag force is not the only interphase interaction force. There are more interphase interaction forces like lift force, virtual mass forces, Bassett forces, and there are lots of others. So one has to understand which interphase interaction forces are acting. In fact, sometimes you have static interaction and some multiphysics happening, that I mean typically particles coalescing or bubbles or particles breaking has a lot of contribution from some other forces as well. So one has to understand that and include that in the model as well. As I said, bubbles can become non-spherical if you increase their sizes, or particles of course may not be spherical, so one has to learn how to deal with that non-spherical shape. Because typically when you develop models from a physics point of view, we tend to take the particles as perfect spheres, but that is not the case. So the relationships will change. And then when we try to model particles as an Eulerian approach, because particles are particles, they're not fluids. Okay? But we tend to use an Eulerian approach for that as well. So for that we have to we use typically a model called the kinetic theory of granular flows. So these particles, flow of particles is typically called a granular flow. So these KTGF models are motivated from your the kinetic theory of gases. Kinetic theory of gases was developed for gas molecules interacting with each other, right? So similar theory for dense gases has been used for modeling particles interacting with each other. Of course, some modifications have been made because there is a lot of dissipation in solid interactions unlike the gases. So that theory has its own terms coming into the picture, like a granular pressure, granular temperature and so on. So one has to deal with those terms as well. So that is another challenge with these models. Right, so now that we have very briefly talked about multiphase flows, let's talk about FEM, finite element method for fluid flow modeling, using an open source code called Fluidity. Of course, we'll be solving multiphase flow problem with that, but before that I just want to touch upon the FEM approach. So in a finite element approach, let's look at what happens in a typical finite element approach. So this is an advection diffusion equation. So you have a transient term, you have a convective term, and you have a diffusive term, and you have a source term. Right? Very similar to the common form of the equation that we have been working with till now. So in a finite element approach, what you do is you develop a weak form of the equation. So you take a test function W tilde, you multiply that with the equation, and you integrate over the complete volume of the domain. Omega is the complete volume of the domain this time. And when you do that, post that you apply the Gauss divergence theorem. I am just telling you the procedure, I am not telling you why this approach is being done. That requires a full-fledged course in finite element methods. Then you apply the Gauss divergence theorem. So you will see that this looks very similar to the way we deal finite volume methods. So this term and this term, the convective and the diffusive terms, get split into these terms, and then you have these terms as well, which where you apply the Gauss divergence theorem, and then this is the boundary of the overall domain now, because you integrated over the complete domain. So the boundary of the overall domain is where you apply the boundary conditions. So now those boundary conditions could be Dirichlet or Neumann depending on what you have, but these terms are dealt with the boundary conditions depending on the boundary condition you have, and this is a part of the equation. So now is where you take the approximation called the Galerkin approximation in FEM. So there you say that these functions W tilde, called the test functions that you chose by yourself, they are coming from the same function space as your solution C. So C is what you want to predict, right? So you say that C is a linear combination of some basis functions phi's. You can do that, right? I mean, in Fourier series, we say that any function can be written as a linear combination of sines and cosines. So basically, our function space in that case is the function space of all sines and cosines. So we tend to write functions as a linear combination of different other functions. So this time we have chosen a function space. I'm not telling you what it is. It could be anything depending on what you want. But you choose a function space. So what that means is whatever functions you want to find out as a solution to this equation will have to come from that space. It cannot come from some other space outside that space. So that is an approximation you are making, and that's not a bad approximation given that you choose your function space properly. So the space of the function space for both the the function C that you want to predict, and it's called the trial space, and this is the test space W tilde functions. They all come from the same space. So the only thing that will differ is the coefficients of the linear combination. The functions phi are the same for both cases. So that when you substitute these two into this equation, then you get this kind of an equation, which basically is a linear equation like this, where this matrices M, A, K are given as this. So you can convert this to a local form from a global form, and then we can take an assumption of what phi's look like. So what typically we do is we take phi as piecewise linear or piecewise quadratic functions. So what that means is, since you have your domain being broken into elements, what you say is that my phi's are such that one given phi becomes is taking a value 1 at the center of a node in a given element, and it goes to 0 within the element. So what happens is the functions will look like these. This is a quadratic function. They look like these tents. So this function is taking a value at this node. You can see that, and it goes to 0, taking a quadratic form from this value 1 to this node. So this at this center node the function is 1, and at all other nodes it becomes 0, and between these two nodes it goes from 1 to 0, and you have lots of functions like this. So there are lots of local functions like this that you have. These are the phi's you have, and using that you predict your solution. So basically your solution that you solve using this will be the coefficients C in this approximation. Basically, if you get the coefficients, you get the function C. So that's what a finite element approach is. So let's now get into hands-on. So now I'll show you in fluidity solving a multi-material, a single phase and a multi-phase, a multi-material multi-phase problem. So I have a virtual machine set up for fluidity. So I'll start that. So first I'll show you the manual for the software. It's an open source software. It's being developed by the contribution from open source community over the last many years. But that does not mean that it does not have good support in terms of documentation and community support. It does have that. Right, so this is the virtual machine. So the first thing we'll do is we'll have a look at the manual. So fluidity is installed. So let me open a terminal, increase the font size. So let's go to the manual folder, and in that folder we'll see, let's look for PDF files. So here we see that there's a file called fluidity manual.pdf, this one. So let's open that. So here's the manual. So if I scroll down a bit, let's go to the table of contents. So it has complete information about obtaining the software fluidity, how to build it, how to make it, if you want to compile it on your own machine, because typically if you want to use it for heavy duty computing on a cluster, you will want to install it from the source code. It's an open source code. So install it from the source code on the architecture that you want to run it on. That makes the executables optimized for the hardware that you're dealing with. Okay, so you can do that. Then how to run fluidity in serial or in parallel. So all these details are there. Then it goes to model equations. What are the equations? How are the equations? What are the equations that are solved in the software? Different types of them. Then what is the numerical discretization? So everything that we have talked about in this course, similar stuff is discussed in this manual. Then it talks about some parameterization, some embedded models, how meshes are dealt with in fluidity. Fluidity has something called adaptive mesh refinement that I'll demonstrate to you, that optimizes the problem, the calculations really well. Then you have some configuration options, how to set up a new problem, different options available, and so on. Okay, visualization and diagnostics, how to, once you have the result files with you, how to extract average properties, plots of different things as a function of time, a space, and so on, and then some examples that we'll be using to understand fluidity. So you can install it on the cluster of IIT Mandi, HPC cluster or Param Himalaya, and remember, fluidity is a solver. Fluidity is just solving the problem. So the pre-processing part, that is generating a geometry and a mesh, is done separately, and post-processing is also done separately. So typically for pre-processing we use Gmesh, the same software we use for generating geometry for our OpenFOAM problem. So we use Gmesh, but you can use any geometry making software of your own choice. Then for meshing also we use Gmesh typically, but again it is your choice. All you have to do is you have to feed a geometry and a mesh to the solver fluidity in a given format. And then once you get the results out of it, the results are in the VTK format, which are readable by ParaView, the same software we use for post-processing the results obtained using OpenFOAM. So they are standard softwares which are well maintained for dealing with large data sets, but there are Python modules available that have been developed to deal with post-processing. So in case you know what you want to extract from the data files, you can simply write Python scripts, and they'll extract the information from those result files and plot them for you. Okay, we'll have a look at that as well. Right, so the first problem we look at is called the lock exchange problem. So it's a single phase problem. In this case, we have a vertical barrier that you can see here between fluids of different temperatures or densities, because different temperatures means different densities, and you have gravity in this case. So blue is the denser fluid, that is low temperature, and red is the less dense fluid or the high temperature. And once you remove the vertical barrier, then what happens is that the heavier fluid tends to flow at the bottom and the lighter one goes at the top, and because of the shear, we have a shear instability being developed here, which results in these spirals called the Kelvin-Helmholtz billows. Okay. It's very interesting. It results in a lot of good mixing between the two fluids, this instability. So these are also, and what you see is basically you see suddenly that the fluid moves like this as two gravity currents. Okay. Without gravity, this phenomena would not have been seen. So we want to simulate this phenomena. For that, we'll be using fluidity. So we will make the mesh, we'll run the problem, we'll make the geometry in the mesh, we'll run the problem, and we'll post process, see the results and analyze some information out of it. And if time permits, we'll also try to modify the geometry and see what happens. So the lock exchange problem is given here. So in case you want to explore things on your own time, you can explore that here. So let's go to the examples folder. So in the examples, So in the examples, we can see that we have many examples. So let's go to the lock exchange folder. So here you can see the results are already there because I already ran it. So what I'll do is I'll do a make clean. Now I've deleted all the results. Now let's go to a file called makefile. It's very useful to have a look at these. So makefiles are a part of something called make language, which is used for build systems. So it helps you automate things. You don't have to worry about stuff. So it says that there certain options are available for you to run. One's called pre-process, one's called run, one's called post-process, one's called input, one's called clean. I just ran clean. So clean basically removes all the result files that is generated by running the software. So it goes back to the situation that you were in the beginning before running the code. Pre-process generates the geometry and mesh. Run will run the problem, generate the results. Post-process will do some post-processing, plotting some graphs and so on. And this is how, these are the three options typically we'll want to work with. So let's close this. By the way, in a high performance computing course that will happen next semester, we talk about how to write these make files, and people who have tried to install something in Linux using some open source code, they would have experienced this option of make, like make install, make run and so on. Okay. So what we'll do is first make pre-process. So now it generates the geometry and the mesh. Now if I do an ls -l, I can see that a mesh is now generated. I can open this mesh in Gmesh like this, and I can see that there is some sort of a triangular mesh, but it looks quite structured. But that's just your choice what you want to do. And near the interface we have really fine mesh in this case. Okay. By the way, I'm doing things really quickly. I don't expect you to follow each and every option. Just see, don't try to remember the commands and so on. We are recording this, but just try to understand what options are available and what can be done in this code. So now we'll do a make run, which will start running the problem. So it sends this command of fluidity with some verbosity, some log file, and then some input file. So it starts running the problem. Let me open another terminal now. Slowed down my machine. It's a gaming laptop, so I have to switch on the performance mode. So now it can hopefully use higher clocking speeds. Okay, so now let's go back to log exchange, and you can see that some files are being generated. In fact, I think it's completed the problem. No, it's still running. Okay, while it is running, I can still post process. So let's open ParaView, and I can open, and I'll say open this log exchange, all the VTU files, apply. So now we see this domain, and I would want to plot the temperature. So this is how the temperature looks in the beginning, right? And now what we can do is we can press the play button, and now it will start to show the simulation of temperature profiles. Temperature is, I mean, it's related to density, it's proportional to density. So you can also assume it to be density. Now let's look at the mesh here as well. So initially the mesh looked like this. Okay. So it did some mesh adaptation, and it realized that the gradients exist near the center. So it refined the mesh near that region. So now you can see the mesh looks really refined in this interface region. In fact, the mesh looks anisotropic. The gradients exist in the x direction, so the mesh size is very small. But in the y direction, the mesh is very large. So the mesh becomes anisotropic. It's not homogeneous. It's not isotropic. It has different sizes in different direction. The elements have different size in different direction. So that's a very useful thing with fluidity and in general finite element codes, that they can deal with these unstructured anisotropic meshes quite well. And in the region where you have no change, the mesh is extremely large in size. And as you run the problem, you will see that the mesh deforms according to the solution. So that's called mesh adaptation or adaptive mesh refinement. It's a very useful thing. It optimizes the computations really well. Okay. And if I switch off this mesh, you can see that this is how the solution looks. In fact, I can now reload the files. Some new files may have been generated. Okay, clear? Any questions?
So this AMR is of dynamic or solver?
Solver. It's a part of fluidity solver. So let's now look at another problem, which is a multiphase. Now here we had only one fluid, except that the properties of the fluid were different. It was having a different density and different regions, but still it was the same fluid. Now what we'll do is we'll look at a multi-material problem, where it's called a standard dam break problem, where you have a liquid and a gas, and the liquid, there is some sort of a dam wall here that prevents the liquid from falling, and then suddenly at t equal to 0 you remove this wall. So you expect the water to enter this right hand side region and show some dynamics, and that is what we are interested in. So let's go back to fluidity. So I'll go to this the problem. The folder is called water_collapse. It's a water column collapse problem. Again, it seems it already ran earlier. Created a copy of that. So let's do a make clean. Let's look at makefile and see what options are available. Again, this time you have make pre-process, run, and post-process. So we didn't try the post-process last time. Let's try it this time. So make pre-process. Let's look at the mesh now. So it's called 2dtank.mesh. So this is how the mesh looks like. So this time we have generated, again looks quite structured but triangular, but only because at t equal to 0 you will refine the mesh according to the solution. So the mesh will change. So let's do a make run, and the problem starts to run this time. And I'll go to a water collapse case that I already have run, because this may take some time. So I already have run this problem. So let's look at the solution. So this is the problem. Now this time we are looking at the volume fraction. So you can see at t equal to 0 you have a volume fraction which looks like this. So you have water in this region and you have air in this region, and if I start to play, you can see that some sloshing of the fluid happens. I'll zoom into it. This time I'll show you the mesh as well, and so you can see this sloshing happening in this case. And you can do a lot of things for post processing in ParaView depending on what you want. I'll leave that for you to explore, but I'll also show you the option of make post process. So that basically is running a Python script for post processing, and when you do that, it generates 2 PDF files as a part of that post-processing Python script, and I can open Firefox. So this is the first graph. So it's a publication quality graph. You can see that. So what's happening is in this flow problem, you had put water depth sensors at 2 different X positions. So what happens is at some position you notice that the water was moving from left to right. So it took some time for the water to reach, and then the water level started to increase as the water was coming from left to right, and then the water moved from to the right, so the water level start decreasing. So this is as a function of time you are plotting the water depth at a given X position. Similarly, this is another X position at which you are plotting, and you can see that there is experimental data available as well, which is being compared to our numerical prediction. So you can see that numerical prediction is good for some region, but beyond that it deviates a lot. So what you can do is you can using these build systems, you can now I can actually have a build system that runs the problem 10 times, generates these graphs with different names, and then it runs a LaTeX file, it puts these graphs into the LaTeX file and generates a final PDF with my report with all the graphs in it. So in case I want to change something, I change it at one point and run the whole makefile thing again, and it will generate a final PDF with my report with all these graphs. So that helps us automate. And right now I was not even worrying about remembering what command to run fluidity, so I can focus on the problem at hand rather than remembering the commands for running fluidity and all these things all the time. So that takes my focus away from other things to focusing on the problem at hand that I want to solve. Right, so that's the end of this very condensed lecture on multi-phase flows and FEM for fluid flows. But the whole idea was for you to appreciate the fact that multi-phase flows are being used in the industry nowadays. In fact, if you look at jobs, a lot of them will be focusing on multi-phase flow modeling. And the other was to help you appreciate the fact that FEM can also be used for simulating fluid flows. Typically, our understanding or our bias is that FEM is for solid mechanics and finite volume method is for fluid mechanics. But that is not the case. You can see that we are solving the same problems quite well. In fact, for some in some aspects, FEM is much better than FV. In fact, FVM, finite volume method, is a very special case of finite element method. If you look at the mathematics of it, it's the lowest order finite element method, that's called the finite volume method. So we can integrate the ideas of finite volume method also, like a control volume approach, into finite element methods. In fact, that is typically what we do. Things which we want to keep conserved, for example, volume fraction, and volume fraction is discretized using a control volume approach, whereas the other things are used or are discretized using a typical finite element approach. So that gives us a lot of freedom to try out a mix of different discretizations and play around with them. And in fact, if you are dealing with a fluid structure interaction problem, then you can use similar finite element methods for solving both the fluid and the solid in the same solver. Okay. A lot of options are available. So we'll end this lecture here now, and if